All right, in this video, we are going to look at linear equations application problems, and what I call motion problems. All these problems involve distances, rates, and times. So start with this example. It says John and Maria are traveling to a concert. The trip takes 2 hours for Maria and 2.5 hours for John since he lives 40 miles farther away. John travels 5 miles per hour faster than Maria. Find their average rates. So as I'm looking at this, one thing that we need to recall from prior knowledge is that distance equals rate times time. That's a formula or a relationship that we're going to use throughout this problem. And so what we actually do here is you don't have to do this, but it's very helpful for me to set up a little table. And our table is just set up to know that distance equals rate times time. And we're going to have one of those relationships. We're going to describe John, and then we're going to describe Maria. And so as we jump into this, let's just read the problem and see how many of these blanks we can fill in. Can we find John's rate? Can we find Maria's time? And that's going to allow us to write some equations. So first off, it says the trip takes 2 hours for Maria and 2.5 hours for John. So for Maria, it takes 2 hours, and for John, it takes 2.5. It also says since he lives 40 miles farther away. That's describing John's distance. So if we describe Maria's distance with just a d, then John's distance would be whatever that is plus 40. That's how we would write an expression to describe John's distance. It then tells us that John travels 5 miles per hour faster than Maria. So if we define Maria's rate as r, then John's would be r plus 4.5. Okay? And now what I've done is just from what's in the problem, I've at least, if I don't know the exact values, I've written expressions for the rates for both, the times for both, and the distances for both. And now we're going to use this relationship that distance equals rate times time. I'm going to write one equation for John and one for Maria, and then let's see what happens. So for John, I'm just going to kind of come to the side here, and we know that his distance is equal to his rate times his time. And we know the same thing's true for Maria. We know that her distance is equal to her rate times her time. And so what we now have is we have two equations, one for John, one for Maria, and it's just a system of equations that we can solve. So what I'm going to do is I'm going to take this first equation and I'm going to kind of come over here to the right and I'm going to simplify it a little bit. So I'm just going to do a little bit of algebra. D plus 40 equals R plus 4.5 times 2.5. Okay? And what I'm going to do is I am going to start off by distributing. I'm going to distribute that 2.5 in, so we have 2.5R plus whatever 2.5 times 4.5 is, and that's going to be 11.25, and that's equal to D plus 40. Then I'm going to subtract 40 from each side. So we have D equals 2.5R, and then whenever I subtract 40 from the constant, we get negative 28.75, okay? And so that's one equation, okay? There's one equation. And then our other equation is pretty simple. It's just hanging out over here. It's just D equals 2R if we want to rewrite it. So the reason I simplified this over here on the right, John's equation, is if I isolate the D there and isolate the D there, then I can substitute. I can set these equations equal to each other, however you want to think of that. So if I have 2R equals 2.5R minus 28.75, hopefully you see that substitution that I did. If both those values are equal to D, then they must be equal to each other. Well, then I'm going to subtract 2.5R from each side. And then I'm going to divide by 0.5R on each side. And we get this. We find the R equals 57.5, but we got to be careful in this type of problem, make sure that we've answered the question. It says R is 57.5. That would mean that John's rate is just whatever that plus 4.5 is. So let me use a good notation here. Let's say the rate of Maria is equal to 57.5 miles per hour. The rate of John is going to be equal to 62 miles per hour. Remember, we got that just by taking Maria's rate and adding 4.5. It doesn't really ask for their distances, but let's go ahead and find them just for kicks. So the distance of Maria is just going to be her rate times 2. So if I took her 57.5 and doubled it, that means that the distance Maria traveled is 115. And that would mean that the distance John traveled is just going to be Maria's distance plus 40. And so that's going to be, I believe, 155. So it didn't really ask for these bottom two values, but we found them anyway. This question was really asking for their rates, and there they are. Let's look at another example. It says Dorian gets to work in 20 minutes on most days. When he rides his bike, it takes him the same route, but he goes 45 minutes. So it takes him longer on a bike. I think that's common sense. His average driving speed is 4.5 miles per hour greater than his average speed on his bike. How far away is his work? Well, once again, we're going to do this just like we did the last problem, except now instead of having two different people, what we're comparing is Dorian's rate on his bike versus Dorian's rate whenever he's driving his car. So we're going to use our little formula that distance equals rate times time. I'm going to set up our little table again. Okay, so we have that, let's make my little box here. The distance equals rate times time. And let's do one for the bike and then one for the car. Now let's just read it and fill in the blanks. It says it takes him 20 minutes to get to work on most days. And it doesn't really say, but when you read the question, it says that here he's driving and here's where he's riding a bike. So his time for his bike would be 45 and his time driving is 20. Okay? Or his time in a car is 20. It says his average driving speed is 4.5 miles per hour greater than his average speed on his bike. So if we don't know his speed on his bike and we just define that as R, then we know that his average speed in his car is going to be R plus 4.5. And how far away is his work? One thing that we know is the distance is going to be the same for both. Now, this question has a little bit of a gotcha. Hopefully you have identified how I already have a mistake in what I've done here. But what we got to be careful is notice that our speed here is defined in terms of miles per hour, yet our time here is defined in terms of minutes. So we could convert 4.5 miles to hour to miles per minute, or we could convert these times to minutes. But basically we have to be in terms of minutes everywhere. So 45 minutes is 45 out of 60. That's going to be 3/4 of an hour. And then 20 minutes, well, that's 20 out of 60. That's just going to be 1/3 of an hour. So let's actually use that. And so I'm going to write our equations over to the side. We have that distance equals rate times time. And for the car, we have that the distance equals the rate times the time. And so I'm going to simplify this right here so that I can... actually, I don't even have to. Let's go ahead and set them equal to each other. If I have that this equals D and this equals D, then those values must be equal to each other. So we have that 3/4 R equals R plus 4.5 times 1/3. Now let's solve this equation. So I'm going to distribute. So we have 3/4 R equals 1/3 R plus 1.5. And then I'm going to, here's where we got to be kind of good with fractions. I'm going to subtract 1/3 from each side. And I'm not going to go into the math of how to do this right now, but whenever you subtract those, if you get your common denominator and then subtract, you should get 5/12 R equals 1.5. So let's kind of come up here. We're not quite done yet. If we have 5/12 R equals 1.5, we could divide by 5/12 on each side. And if I do 1.5 divided by 5/12, that's going to give me a rate of 3.6, okay? And what that means is that his rate riding his bike is 3.6 miles an hour. So let's use our notation again. Let's say the rate on a bike is going to be 3.6. That means his rate in a car is going to be that 3.6 plus 4.5, which is going to give us 8.1. And then for the distance is going to be the same in the bike as in the car. And all we'd have to do is we could use either one of these equations. It doesn't matter which one. But if I take that rate, R, the rate in the bike, and multiply it by 3/4, that's going to give me that the distance is equal to 2.7. If we did this right, that would give you the same thing if you used it in this equation down here.